Cool. We are live on YouTube. Yeah. So let's let everyone in. I'll also record on Zoom as a backup. Let's wait a few more minutes. Seems like people are still coming in. Okay. I say let's begin. Lorenzo, you're muted.
Yeah, great. Okay.
Okay.
That's
So hello everyone. Welcome to the first KISS seminar of this academic year. I have the pleasure to introduce Lorenzo Maccone from the University of Pavia. He will talk to us about a topic in the interface between quantum mechanics and relativity, as is proper for KISS. Yeah, it's called geometry-based quantum mechanics, right? So, Lorenzo, the stage is yours.
Good. Thanks. Thank you very much. Thanks for the kind invitation. I'm very happy to be here. So this is work I did a couple of years ago with Seth and Vittorio. I've been working a lot on this recently, especially this summer. I really did a lot of work on this, but I'm not ready to show the newer results. So I'll just present the framework. So the idea is this geometric event-based quantum mechanics. And why are we interested in that? So let's start really from the basic foundations of the quantization of relativity. What is the problem? Why is it so difficult to quantize general relativity? And there are also problems with special relativity. Well, if you look at how the theories are constructed, you see that quantum mechanics is a theory that describes quantum systems, whereas relativity is a theory that describes events. So, of course, there's a difference because events are finite in space and in time, whereas systems are objects that are infinitely extended in time and can be finite or infinite in space. Like, if you're looking at a spin, typically you look at the time evolution of the spin. It goes from minus infinity in time to plus infinity in time. And so you find out that if you think about it, our two main theories, quantum mechanics and relativity, talk about different things. And I believe that this is the reason why sometimes it's difficult to merge these two theories. So these two concepts are very related, of course. Once you define one, you can define the other. Which of these two is the most fundamental one? What do you think? Is it a system or is it an event? Of course, once you define a system, you can define an event as something that happens to a system, no? And on the other hand, once you define an event, you can define a system as a succession of events, like a timeline. These are the definitions you find in relativity, for example. So now, of course, once you have two possible approaches, depending on which of these two things you consider as the most fundamental. If you say that systems are more fundamental, then you can have a general relativistic theory of quantum mechanics. If you think that events are more fundamental, you can try to do a quantum theory of general relativity. And of course, as I was saying, if you take the vision that systems are more fundamental, then an event is what happens to a system, so it's a derived notion. And on the other hand, if you take events as more fundamental, a system is just a succession of events, a timeline. Okay, and of course, if you look at all quantum gravity approaches up to now, all the attempts or even quantum field theory of trying to quantize, to merge relativity and quantum mechanics, they all did the first thing. I mean, they start from textbook quantum mechanics, where the systems are the most fundamental thing, and then they try to create a relativistic theory out of that. Well, of course, the object of this talk and of our theory is to explore the alternative. So try to make a quantum theory of events. So this is why it's called an event-based quantum mechanics, because it's something that starts from events. And it's called geometric for reasons that we will see. Basically, the reason why it's called geometric event-based quantum mechanics is because in this theory, we will see that Lorentz transformations are really nice geometric things, like you would expect. Current quantum mechanics is really not geared towards this kind of vision. So if you look at the classical picture, you have space-time, as usual in relativity, time goes up and space goes left or right. And an event is just a region of space-time. A system is a succession of events, like a timeline. Well, this is the classical picture that you will find in any relativity textbook. In quantum mechanics, what happens? This is a particle in a quantum superposition of two counter-propagating Gaussian wave packets. And they meet here at this space-time location. And of course, you have some interference fringes because you have quantum superposition. And the fact that quantum mechanics is a theory of systems and not of events is reflected into the fact that in this picture, the situation has a normalization at all times. So basically, you know that the particle will be found if you take a time slice, it will be found somewhere at all instants of time. So this is normalization of a wave packet. The integral over all space of psi mod square is equal to 1 at all times, for all times. Of course, you see immediately, first of all, that there is a fairly definite distinction between space and time here. I mean, clearly time goes up, the fringes are oriented along time and not along space. And you can start, if you look at this picture, you maybe can start to ask yourself, well, trajectories in space are ill-defined in quantum mechanics. Indeed, you see that there are points in the space where the particle will never be found. Like these, here you have destructive interference. You will never find the particle in these antinodes here. So, of course, the particle that propagates doesn't really have a trajectory. Why should it have a trajectory in time? Why should you ask for the particle, for the wave function to be normalized at all times, for the particle to be found at all times, if you are not asking that the particle should be found at all positions? Okay, so this is already something that maybe from a relativistic point of view, you don't find very exciting. Okay, so now how we go beyond this picture. And the idea, which we will start, is to construct kinematically a Hilbert space for events. Instead of a Hilbert space for systems that you find in textbook quantum mechanics, we require a Hilbert space for events and its composition rule and all that. Let's start with special relativity. I mean, GR, already special relativity, as you will see, is quite complicated. I mean, everybody that has opened the quantum field theory textbook knows that. So let's start from that, and then we'll deal GR in the future, with general relativity in the future. I mean, I've been talking to people on how to extend this framework in general relativity, and we have some ideas, but okay. Let's start with special relativity. So textbook quantum mechanics uses quantities which are conditioned on time. This is not explicitly written in textbooks, but if you think about it, you'll find that it's true. So the states, for example, if you work in the Schrödinger picture, psi of t is the state given that time is t. So it's a condition on time. It's a state which is conditioned on time. And similarly, the observable is, if you work in the Heisenberg picture, is the position observable given that time is t. So it's a time conditioned quantity. Okay, and this you can see because if you take the Born rule, so if you take the square modulus of the scalar product between this state and the eigenstate of the observable, this Born rule gives you a conditional probability, the conditional probability of finding the particle at position x, given that time is t. This is the reason why textbook quantum mechanics really is using conditioning. time condition quantities. So this means that really these quantities, the Born rule probabilities, the states, the observables, cannot be in itself relativistically covariant because they are conditioned on time. So you need, that's what you do in quantum field theory, you need to start from a foliation, and then given a foliation, of course, the foliation can be arbitrary, but you need to start from a foliation of space-time in order to even write your states and your observables. Okay, so in itself, this picture cannot be covariant. You need to work a little bit on that. Of course, quantum field theory is a covariant theory because, first of all, the foliation can be arbitrary, and then you also use a couple of tricks to recover covariance on site. For example, you use, well, you work in the Heisenberg picture, which is weird because Heisenberg picture and Schrödinger picture should be equivalent. And then you use observables that in the Heisenberg picture have a covariant space-time dependence, for example, the creation or annihilation operators, which have a time dependence which can be put in covariant form. And then as states, this refers to observables, and then as states, you use states which are invariant under Lorentz transformations, typically the vacuum state, which is left invariant under Lorentz transformations. Okay, enough about what people usually do. Let's talk about what our approach is. So our approach is called geometric event-based quantum mechanics, GEV, where, as I said, we take quantum events as fundamental, and then quantum systems are derived, a quantum state for a succession of events in quantum space. We will see how that looks like in a minute. So what is a quantum event? Well, okay, an event has some type of, must have a position in space-time. So this is what defines an event. It has a location in space and a time at which it happens. But you also have to attach some energy and some momentum to your event because otherwise nothing would happen. Without energy, nothing can happen. Without momentum, nothing can be really localized because of the uncertainty relation. So not only you need a position, but in space-time, you need also some energy and some momentum. Okay, this means that kinematically we can define some basic observables for the quantum events. So a space-time position observable, this X, the overbar here denotes that it's a 4-vector. Okay, this is the notation I use for 4 vectors. So it has a time component and a space components, and then this is the energy and the momentum, okay? And now we quantize just by using canonical commutation relations, of course. So the commutator between x mu and p mu is equal to minus I h bar. Well, h bar is equal to 1, minus I h bar eta mu, where, of course, this is the Minkowski matrix, and we use the Minkowski matrix in the canonical commutation relations because we want a covariant theory and also because we want the Poincare algebra. So if you define position and momentum in this way, this m mu, which contains, which is the generator of rotations and boosts, so the angular momentum satisfies these commutation relations, okay? So this is pretty straightforward. Note that P0 is the energy, it's not the Hamiltonian. So the Hamiltonian is something that comes from a dynamical, something dynamical. The fact that the energy is equal to the Hamiltonian, that's a dynamical statement. For now, we're just looking at the kinematics of everything. So this is just the energy, not the Hamiltonian, at least not yet. Okay, and now we have these observables. We can take their eigenstates. So this ket here is the eigenstate of the position, of the space-time position observable. This ket here is the eigenstate of the form momentum observable, and then you can introduce a generic state just by using the superposition principle. Oops, somebody has a question. Should I take questions now?
It's your decision. You want to take
Yeah,
questions?
sure. Go ahead.
Yeah, hi, Lorenzo.
Hi.
It's very nice to be in a seminar given by you.
Thanks.
I've been a big fan, especially since I saw your paper from many years ago on the origin of time as a succession of events. I forget the exact details, but anyway, my
Right.
question about the present is that you're taking space-time to be a given, right?
Yeah.
Okay, yeah, that's what I wanted to ask.
Yes. So you have you could add some quantum reference frame and so on and so forth, but we are not interested in those kinds of things at these levels. So you have some space-time which is measured by some reference frame, which is classical and which allows you to write these kinds of integrals. So space-time is given, and then you're interested in this space-time to look where and when these quantum events happen. Okay, very well. Okay. So, of course, this is a generic state. You can just write using the superposition principle, starting from these observables are introduced. But of course, not all these states are physical. Not all these states are something that you will see. For example, the eigenstate of the space-time location is just describes like an event that happens in some space-time location and then nothing else in the whole universe. Okay? So it describes that, for example, suppose the event is a detection of a particle, of an electron, say. This eigenstate is just a flash of this electron, which just appears out of nothing. You find it there and it disappears into nothing. That's not something which is physical, right? You cannot really describe a quantum system. But notice that we don't care. It can describe a measurement apparatus. So it's a measurement apparatus, which is the apparatus which measures the space-time location of events. Okay, it cannot describe a quantum system. Remember that the system is a succession of events. Here you don't have any succession. You just have a single event. But it can describe a measurement apparatus, which is something which is very nice. The physical states are ones that satisfy some constraint. We'll get back to that. For example, the Wheeler-DeWitt constraint, Page and Wooter's theories and things like that. We'll get back to that. But let's stay for now in the kinematics. Of course, these are probability amplitudes, which we have used to do the superposition. And they are amplitudes, they are wave functions. This is the position representation, this is the momentum representations, and they are connected by this four-dimensional Fourier transform. Okay? And of course, the Born rule is just the square modulus of the wave function. This tells me that the probability of seeing the event in a space-time location given by this 4-vector x is given by this pi mod squared. Okay, notice that this is unconditioned. This probability is not conditioned on the event. It's just on the time, so it's unconditioned. It's just a probability that the event happens at this space-time location. Whereas if you take textbook quantum mechanics, as I was saying earlier, the Born rule is a conditional probability because it's a probability that the particle, because you're not looking, or the system, you're not looking at events in textbook quantum mechanics, is at some location, let's say X, given that time is t. Okay, so it's condition. So quantum mechanical probability, textbook quantum mechanical probability are not covariant because you have to be careful because they are conditional probability on time. And indeed, if you look carefully in quantum field theory textbook, you never see the claim that probabilities are covariant. I mean, I found that claim, but it's not in the major textbook. Whereas by construction, this modified Born rule in our construction is okay. Now, one of the consequences of this canonical commutation relation, of course, is given by the uncertainty relations. So you get that with the usual Robertson derivation, you start from the commutation relation, you get the uncertainty relations. And of course, for mu equals 1, 2, 3, these are the usual commutation relation between position and momentum. For mu equals 0, you get a time energy uncertainty relation, but it's very different from the usual textbook time energy uncertainty relation. Here, you get it as a consequence of the commutation relations. So it's really a Heisenberg-Robertson type of inequality of uncertainty relation. Whereas in textbook quantum mechanics, this type of situation is completely meaningless. The time energy uncertainty relation, delta t is not an uncertainty because time is a parameter. It's a classical parameter. It's not an observable in quantum mechanics, so you don't have any intrinsic uncertainty in textbook quantum mechanics. When you see delta t, delta p greater or equal than h bar over 2, in textbook quantum mechanics, like the Mandelstam inequality, delta t is not an uncertainty in time, it's a time interval, okay? And the correct interpretation of the time energy uncertainty relation, of the Mandelstam time uncertainty relation, it's more like a quantum speed limit. It tells you that the time it takes, the time interval it takes for a system to evolve to an orthogonal configuration, if it has an energy uncertainty delta E is greater or equal than this kind of inequality. Okay, so this is already something nice, and the meaning of the time energy uncertainty relation in our construction is that you cannot really localize an event in time unless the energy devoted to this event has some energy spread. And this is very different from the textbook interpretation of textbook time energy inequality. Okay, another nice consequence of our theory is that the Lorentz transformation.
Lorenzo, there is a question in the chat.
Ah, sorry, I didn't see that. Okay, sure. What is the question, Ken? I don't see the chat.
So the inner products. So the question is, the inner product, the amplitude of field states in QFT seems not to be simply the probability when we generalize quantum mechanics in special relativity case, and the scattering amplitude is Lorentz covariant.
Of course. So when you're taking scalar product of field operators, these are operators. Okay, so they're not states. I'm talking about scalar products of states. The Born rule, the probabilistic content of quantum mechanics comes from scalar product between states, the state and the eigenstate of an observable. Okay, that's how you calculate probabilities in quantum mechanics, also in quantum field theory, of course. What the person, sorry, I don't know his name because I don't see, or her name because I don't see the chat. What the person is talking about is scalar product between operators. So in order to get the probabilities out of that, you need to put states inside. Typically, you put the vacuum state. and then you have scalar products of probabilities, and then what I was talking about applies. Okay, I hope this clarifies. Let me see. I should. I don't know how to.
Yeah, no, but when you do it, then part of your screen is we cannot see it because
Okay, yes. So maybe I
you're only
should
window.
move it on the second screen.
So yeah, I
Now
can
you can see
create
you
another
can see
one.
the screen.
Yes.
Okay. Okay. Jan said now I see the chat. Okay, great. I hope I answered to the question. Okay, very well. Let's go on. So I was saying, so I'm almost out of time, right? I should talk for 40 minutes, you were saying, right?
Yeah, we started at 4:05. There were a few questions, I guess.
Okay, like
20
15
minutes or
minutes.
so.
Okay, okay. Good. So I won't be able to finish all I wanted to talk about, but doesn't matter. I mean, the important thing is to give the main message. Yeah. So another nice thing about this construction is how Lorentz transformations look like. So I was saying the G in JEB is due to the word geometric because Lorentz transformation are just geometric unitary transformation on the state. Okay, and this is really a beginner's prescription on how to describe the symmetries of a theory. You want to have a unitary applied to the quantum state. You do the same thing in relativistic quantum mechanics, although you have the problem I was talking about, that this is really not, I mean, you have to take the spatial part of the Lorentz transformation when you do that. It's more complicated than that. Here, it's very simple. You take the state, you apply a unitary transformation to the state, and that describes a Lorentz transformation. Okay, it's just very geometrical, just like you would expect from a relativistic field. In quantum field theory, what happens? It's very complicated. If you want to apply a Lorentz transformation, you really need to, since you define states and observable on some predefined foliation, you need to do the Lorentz transformation, then redo the whole quantization from the start in the new frame with the new foliation and rerun the quantization procedure. So it's really much more complicated. Okay, and let me skip this. Okay, so up to now we looked at the quantum state of a single event, something that happens somewhere in space-time. But of course, that's very boring. You want to describe multiple events in order to do something useful. And of course, you just use the usual prescription of quantum mechanics to describe in quantum mechanics to describe multiple systems. You use tensor products. Here, you use tensor products to describe multiple events. Okay, so you just generalize the wave function. This is the joint probability amplitude that the first event happens at space-time location x1, the second x2, and so on up to xn. Okay, this you can do that if the number of events is fixed. You already know that you have n events, then you can use tensor products. If you don't know the number of events, that's itself a quantum number, a quantum thing, then you can use Fock space. So you introduce some creation operator that creates some event at position x1, x2, and so on. And this is vacuum state, so it describes a universe with no events, and then you apply this creation operator. And you see immediately that this wave function now is it's a joint probability amplitude. If you take the mod square, it's the joint probability for the n events to happen at these space-time locations. Okay. Here I also introduce these sigmas, which represent some internal, possibly internal degree of freedom, like a spin or something. And notice that here in this probability amplitude, each event has its own time. Okay, because of course you're looking at n spacetime events. It's amusing that one of Dirac's papers, one of the first papers on relativistic quantum mechanics, had a sort of a wave function of this type, but Dirac was in trouble because he couldn't really understand how to treat all these n different times, because of course he was thinking in terms of systems. He was using conventional theory, and I mean, in conventional theory, you have a single time. Here you have n times when you write this kind of thing. So Dirac amusingly just says, okay, let's take all the times equal. Just like that. Okay, fine. Good. Okay, so you have this Fock state, and then you can impose commutators or anti-commutators between these creation and annihilation operators. If you use commutators, you get bosonic events, which give rise to bosons. If you take anti-commutators, you get fermionic events, which give rise to fermions. I mean, I'm going very fast now because these are all more like technical details. You can find details in our paper. This is the 4D vacuum in the sense that it describes a universe where nothing happens. You don't have any events. And it's, of course, very different from the 3D vacuum of quantum field theory. In the vacuum of quantum field theory means that there are no particles at some time, okay, just because, as I was saying, in quantum field theory, you need the foliation in order to define your states. And you typically work in the Heisenberg picture and sometimes in the interaction picture. And in the Heisenberg picture, the state that represents the state at time t equals 0. So, okay, the QFT vacuum tells you that there are no systems or no particles at time t equals 0. This instead is a state which describes a whole universe at all times, but with no events. And of course, you can go from one to the other in this way. You create an event with 0 for momentum. Okay, this creates a universe in which there is a single event with 0 energy and 0 momentum. And then you just foliate. You take just the spatial part and you get the 3D value of that. Okay, so now, I was saying that in order to describe the physical state, you need to introduce the constraints. Up to now, we have been looking at the kinematics of this construction. Now we want to introduce the dynamics. So how can we describe dynamical laws and what happens? As I was anticipating, the idea is to use constraints, as in non-relativistic quantum time approaches, like the Page and Witter's approach, the quantum time picture, which now is becoming very fashionable, or even before the Wheeler-DeWitt approach, in which you introduce the dynamics using constraints. For people who are more familiar with quantum field theory, maybe you can think of Gupta-Bloiler formalism. Also there you say, okay, the physical states are the ones that satisfy some constraints, and the non-physical states you just discovered. So this is the idea. And so the idea is you start from some state, and you introduce a constraint, which this is an operator, this K operator contains the whole dynamics, and you say, okay, it's a physical state if it satisfies this constraint equation. Okay, you can think of this as a Wheeler-DeWitt equation, for example. And for example, if you want to obtain like the state of the dynamics of some quantum system, okay, you can start from a single particle wave function. This is the wave function that describes, so this is the one you would find in conventional textbook quantum mechanics. So it's the probability amplitude that the particle is at position x, given that time is t. Okay, you start from that, and then you just promote this conditional probability amplitude, you promote it to a joint probability amplitude. Okay, just like that, you say, okay, instead of considering this as a conditional probability amplitude, we define it as a joint probability amplitude. And then this is the probability amplitude for the Jeb construction, for the Jeb state. It's a state of this type. This punctuation mark is just because there's a subtlety here. If you do that, the state you obtain here is not anymore normalized. Okay, but that's just a subtlety. Anyway, so this is a way in which you can start from the dynamics of a textbook system and derive a Jeb version of it, a geometric event-based version of that. You transfer a wave function into some quantum superposition of a succession of events at all times. Okay, this is the way to do it. And of course, you can write this as an eigenstate of some constraint operator. You can always do that. And this is the way to introduce the dynamics in the whole construction. Okay. For example, this is the Klein-Gordon constraint. I'm just flashing it. It would take too long to really discuss how you would derive that. You can find it in our paper. In our paper, we also have some description of the Dirac equation. There are some issues, I think, with the Dirac equation. I've been trying to work them out. So let's restrict to the Klein-Gordon equation. Okay, so this is the main things I wanted to give you. So the main ideas that we obtained. Before closing, I want to make it very, very clear that I'm not saying that quantum field theory is incorrect. Okay, of course, quantum field theory is correct. It would be crazy for me to claim that QFT is incorrect. This construction is just an alternative way, alternative in the sense that a different way to obtain the same results. So why would you do that? And the reason is that maybe this gives you a better ontology. Maybe you can really get a better physical picture of what is really going on in relativistic quantum mechanics with respect to QFT, which is kind of opaque in some descriptions. And maybe, hopefully, this opens the way to go further than quantum field theory can go. I mean, maybe we can get some result. I mean, quantum field theory has some conceptual problems, and maybe this alternative approach can solve them. I mean, that's my hope. Okay, conclusion. So I talked about this Jeb, geometric event-based quantum mechanics, which is a new approach to relativistic quantum mechanics. It starts from the idea that quantum events are the fundamental entities, and then you construct from that, you construct observables, Hilbert spaces, Fock space, bosonic and fermionic events. This is all kinematics. And then you introduce the dynamics by using constants, okay? By the way, one other nice thing of this construction with respect to quantum field theory is that in QFT, there's no real distinction between kinematics and dynamics, because quantum field theory, you're really quantizing the solutions of your dynamics. So really, you don't have a kinematics and then a separate dynamics. You're really doing it all in a single step. Here, instead, you're doing it in two steps, which is, in my opinion, preferable. Okay, so this is the take-home message, this new approach to relativistic quantum mechanics. This new Journal of Physics, if you want to see the details, is where we publish these results. Thank you very much.
Thank you, Lorenzo. This was very nice. Oh, I see there is new animation in Zoom for applause. Nice. We already have a question in the chat, and if other people have questions, they can raise their hand. This is how we do it usually. So can you read the chat? I will read.
Yes. No, I have it. So this will be an effective theory parallel to QFT. Yes, the high precision of QFT does not mean it's totally correct, but in such accuracy, all the theory combining certain features will give the same result. I'm not sure what you mean by effective theory, but if I understand your question, the answer is yes. This is parallel to QFT in the sense that it's a different approach to the same physics, the same underlying physics. So maybe ideally you should get the same results. If not, of course, this would mean that this theory is incorrect. I mean, or maybe this theory is correct and QFT is wrong. I don't know, but I don't think so. This is not going to happen. QFT has been really tested to amazing precision, so it's very difficult to claim that QFT is incorrect.
I have a question.
Sure.
Can you go back a few slides to where you rewrote a quantum system as a sequence of events?
Yeah, sure.
So it looks like it is one event because
Yes, that's right.
but
That's right. If you think about it, how do you see an electron? When you have an electron, you don't see the trajectory of the electron in time. You see a flash, a single flash on some scintillation screen or some position. So the whole electron is described by a single event. Okay, this is the idea.
Okay, so this thing does not describe the electron per se, but like
Yes, it describes the electron per se, but it doesn't describe the whole history of where the flash that describes the detection of the electron will be.
but then it means that the time of detection has some probability distribution.
Yes, exactly.
What is the physical reason that this
Okay,
thing is different?
it's not a description of a detection in which you switch on the detector at some time t. Okay, that would give you a conditional probability amplitude. If you have a detector that you switch on at a certain time to look where the photon is, the electron is, that will give you, the time would be a parameter in your measurement. Okay, I'm switching on the detector at some given time and look at where the electron is. Here instead, also the time is a dynamical quantity. So you keep everything on, and at some random time, you get a flash, okay? And a flash in some location that tells me where and when the event of the electron detection happened. So both the time and the position have some probability distribution, exactly like you said.
Okay, and will there be any meaning to describe a continuum of events that would then have a probability distribution to be different timelines, different world lines of the particle?
You mean, I mean, like what you see how do you call this? The trajectories you see in these super saturated experiments where you see a line of droplets. Is that what you're asking?
No, I was just thinking to have like X and T.
Oh, X and T. Yes, you have
Then you
X
have
and
a
T.
world line that shows you where the
Yes.
particle was.
But here, the world line is a world line which is very different from the classical picture. Let me get that back. So in the classical picture, you have a world line of this type, in which at each time you have a position, okay? In conventional textbook quantum mechanics, you have a world line of this type, in which at every time you don't have a specific location, but at every time you know that the particle is somewhere. Okay, so this is another picture. The picture I'm talking about, I should draw that, is something where you can also have interference in time. Okay, so you have like interference fringes both in space and in time, and you just have a joint probability amplitude for the event to happen somewhere in space-time. That's all.
Yeah.
That's what this this state really is telling you. The state you were asking about.
Okay. So it's not only that the events are now fundamental and not the system, but you turn the systems into events and not into a
Exactly. So the square modulus of this would give you the probability that you see a electron detection event at some space location and at some time. That's the idea. It describes a whole electron at all times, but it describes it in a way by giving you the probability amplitude to detect that electron at a certain location at a certain time. That's the way it describes the electron.
And I guess that getting the world line will come from assuming that I have some measurement apparatus that
the world line is just because here you have the whole thing. You're integrating, this is a 4-vector, and you have a temporal component in this integral.
Yes.
So that's where it comes.
Yes, but and how do you reconstruct world lines? Because at the end of the day, we do see them in the lab.
You don't see world lines. I mean, if you repeat the experiment many times, that's what you're asking, right? So it's the same as you would reconstruct the position of an electron at a given time. You just repeat this experiment. You prepare the electron many times in the same state, and then at the same time you measure it, and you get a distribution, a probability distribution, which gives you this mod square of this probability amplitude. But time is a parameter because you're switching on the detector at a given time, and repeatedly you're recovering the position of the electron, and you get a distribution out of that. Here we're doing exactly the same thing, but you're not switching on the detector at a given time. You're also measuring the time at which the event happens. But the idea is exactly the same.
Yeah. Okay, great. Thank you, Lorenzo. So the first question was from Gaetano.
Okay.
Hi, Lorenzo. It's
Hi, Gaetano.
Yeah.
Hi.
Sorry. Can you clarify the meaning of the form momentum of an event? I mean, from the physical point of view, how would you measure it?
How would you measure it? I don't know how. I mean, in practice, I don't know, but it just describes the energy and the momentum that is assigned to some event. So every time something happens, it means that you must have an energy and you must have a momentum. That's I'm not sure. So this is the energy. Okay, you see a flash, you measure the energy of that flash, that gives you this P0 component, and this flash will give you a kick to your detector, and this gives you the momentum. I don't know. I don't know if this answers the question.
Well, the flash is in all directions, so
yes. You have to collect the energy and then
So
Then,
I could, if you measure the total momentum of the radiation, it should be zero, maybe, probably. But
zero?
then
No, no,
it's
no,
not
no, 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 it's not zero, of course not. No, no.
the three momentum.
Ah, the three momentum. Yes, yes, maybe.
So
Yes, yes,
this
yes.
is not
That is.
compatible with the P dot P being an invariant. I mean, if P0 is different from zero and P is equal, the three momentum is zero, this is not, I don't, yeah, okay.
Well, in order to measure this, you have to, of course, measure this on some state. Okay, so this is just the observable. So now you have to create a state, and then the measurement you get from this probability amplitude. Okay. It gives a probability amplitude to have some energy and a probability amplitude to have some momentum. It depends really on how the state is constructed. And this depends on the dynamics you're using and so on and so forth. So you can have zero momentum, you can have any momentum you want. Depends on the state.
So you're saying that measuring or defining what is the form momentum of an event, which is
Yes.
part of the kinematics, depends on the dynamics?
No, it depends on the state, and this is all kinematics. And then how you construct the state depends on the dynamics, of course. So
But
the measurement is just kinematics, as you say, that's right. And it just depends on the state. But how do you choose the state? You have to introduce a state that satisfies some dynamics, some initial conditions, and so on and so forth. And that's where the dynamics comes in.
mhm. I think that yeah, okay, this question is very interesting because usually we are used to think that location is something that both the physical system can have, a mass can have a location, but the location can also be just someone pointing out somewhere on the map. So the space-time
Yeah,
point itself and not something that happens there.
yeah,
But
yeah.
momentum, the point on the map usually does not have a momentum. Only an actual particle has.
Yes, that's right.
But
That's right.
here you're saying that no, we want
Yeah,
to the point on the
yeah,
map.
yeah. But this is just the usual duality between position and momentum.
Yeah, it's just
It just comes out from that.
yeah,
I mean, and this is a consequence of the canonical commutation relation. That's where it comes from. Sorry, I've lost them. Well, anyway, you have a Fourier duality between position and momentum. In this case, it's promoted to a Fourier duality between for position and for momentum, but it's just that. It's just that. Nothing. Here it is. It comes from the canonical commutation. Imposing these commutation relations means there's a duality, a Fourier duality between position and momentum. And that's it. Nothing more, nothing deeper than that.
yes, yeah, it's the same way that it is in quantum mechanics.
Yes, exactly.
But
The only difference is that here we're introducing also the fourth component. That's all.
yeah, so that in quantum mechanics, as Gaetano said, you would think that uh, if a particle has a location, then okay, it also tells you that it has some distribution in its momentum.
Yes, of course.
It's just the Fourier transform. But then you can actually think of an experiment that would measure this momentum. And we would also have an intuitive understanding of what it means classically.
Yeah, yeah.
But do you think there is any classical analog to a momentum without a particle, like a smile without a cat?
Momentum without a path. I don't. Why are you saying a momentum without a particle? You can always go from one to the other by Fourier duality. So I'm really not understanding your
Yeah, no,
question.
mathematically you can go from one to the other, but if we say that this cat X is not in the GEB, but it is in textbook quantum mechanics, and it describes a particle which is localized
Yes.
somewhere, or
And
maybe
here,
localized, maybe it has some distribution.
yeah,
Then we would be able to understand the classical analog
sure.
of what it means to have, what is the other side of the equal sign? What is this
Yeah,
moment? It means that if we put something there, it will give us some kind of a kick that we
yeah,
can.
yeah,
But would the
exactly. Here,
event, without having, would the event, just the point of the map, also give
yeah,
us?
yeah, yeah. No, the event is not a point on the map. This is a physical event. Okay. So it's something that happens, something that really happens. Okay.
Aha, it's something
The,
that
the
really
point
happens.
on the map would be your reference system, which is hidden here inside this integral. Okay. This ket is not some abstract point in space-time. This is the position of some event. Okay. That's a good point. That's a good point.
Ah, okay, I understand now. Okay, okay, okay.
No,
So
no,
it's
the,
actual
the
flesh, an actual thing happening. Okay.
yes, yes, an actual thing happening. Otherwise, what you're talking about, a position in space-time, an abstract position in space-time, that's just something which is in the reference frame, which here we're not really giving a quantum description of, and it's intrinsic in the integral, if you want. In order to write this kind of integral or this ket, you need to establish a reference frame and so on and so forth. And that's where the abstract notion you were talking about lives. Yes.
Uh-huh. Okay, okay, okay. Okay, so this is also new compared to relativity, because in relativity, an event is really just a point on the map of space.
That's a good point. Yes, yes, that's right. That's right. Yes, that's a good. I never thought about that. Yeah, yeah, that's a good point.
Okay,
Yeah,
thank you.
yeah,
So let's
that's
go
right.
to the next question by Fedele.
Yeah. Yes, ciao Lorenzo.
Ah,
Uh,
sure,
there is something I don't see. Is there a
sure.
way for which particles don't disappear? So in usual quantum
Yeah,
mechanics,
good point.
transformations are unitary, so they preserve probability. And so
Yeah,
if you have
yeah,
something, it can do whatever you want. But
yeah,
if you start
yeah,
with one
yeah,
particle, you will end up with
yeah,
one
yeah,
particle. Here,
yeah.
I don't see how things that cannot
Yeah, you don't see
can
because it's
disappear or appear.
exactly. You don't see because it's not there. At the kinematics level, exactly as you say, things can appear and disappear because time is really a dynamical variable. There's no unitary. Okay.
Mhm.
If you want to put the unitary, and typically you do want to put the unitary, then it must go inside the constant equation. It's a dynamical statement. Okay.
Okay.
So you want to do that, then you have to put the unitary here in this dynamic in the constant equation. Okay, and typically what happens once you have a unitary evolution, what happens is that the temporal part of this probability amplitude becomes a constant because, as you say, you have a conservation of probability. This is why here we take a conditional probability amplitude and we promote it to a joint probability amplitude. From the Bayes rule, you're just taking a constant probability over time, which is what you would get from unitary evolution. Okay. Yes, that's a very good point. Yes.
Okay. Just a comment on the previous discussion.
Sure.
When Ovek was saying you can point on a map to a position, well, all you need is to find yourself a map of a phase space, and then you will point to a point on the map on phase space will be a position and momentum. So it's just that we are used, of course, to maps of configuration space because it's what we have on our telephones with Google Maps. But you can have equally well in quantum mechanics a map on momentum space, and this will give you all the feature of quantum mechanics is that the knowing the probability in momentum space with the fact that they are complex numbers, of course, it gives you all the information. But there is a perfect duality in usual quantum mechanics, and I think also in the model that Lorenzo is describing between position and momentum. And but what I don't grasp completely is the complete duality between time and energy. And there I end up with the usual problem of Pauli, I think it was Pauli, yes, the fact that the spectrum of time goes from minus infinity to infinity, while energy being related to Hamiltonian, so
Exactly.
do you have a problem in that department as well?
No, okay. I mean, I wrote a whole paper about that. So these kinds of frameworks can go beyond that situation. And the trick is the following. The trick is to okay, so we can look at it from the non-relativistic perspective or from the relativistic perspective. Let me start from the non-relativistic perspective, which is easier, okay? So in this case, you have, you can add time as a degree of freedom, and this is the Page and Wutter's construction, for example. And there, time becomes an observable, Hermitian observable. And of course, as you say, if you have duality between time and energy, then it means that the Pauli objection says that the energy should be unbounded from below and infinite, but infinite spectrum. But what happens really is that you have a temporal degree of freedom, a clock, if you want, that describes the time. And this clock, it has an energy which is unbounded, but the system Hamiltonian instead lives in a different Hilbert space, and it can have any spectrum loop. Okay, so this is the idea. So you can go beyond the Pauli. I mean, just in short, I'm not doing a very good job at answering you, but in short, you can go beyond the Pauli objection just by realizing that the temporal degree of freedom and the Hamiltonian live in two different Hilbert spaces. Okay, so then this works.
Okay, we had another question from the chat. Arno is asking, from the geometric event-based in the title, I'd expect a classical approach to QFT, but yours is rather an application of QFT tools to the classical notion of an event? Question mark, rather philosophical. Sorry if I missed this.
Classical approach to QFT. I don't know what you mean by that. This is just, it's the opposite, I would say. A completely quantum from first principle approach to relativistic quantum mechanics. In QFT, you start from the classical dynamical equations, and then you solve them, and then you quantize them. So QFT really starts from the classical things, and then you quantize them. Here, you do the opposite. You start from the quantum kinematics. From really the beginning, you start quantum, and then you introduce all the layers you want. Okay, I don't know if this is answered your question, because I don't really understand what you mean by classical approach to QFT, but this is not. This is a fully quantum from first principle approach to relativistic quantum mechanics. More quantum than QFT, because QFT really starts from classical dynamics, and then it quantizes the solutions.
Yes, yeah, that's clear. Thanks. By classical approaches, I mean something like what Toft is doing, like cellular automaton approaches.
Okay,
and
I
stuff
see. No. Okay, no.
But
Okay,
it's clear.
that's-
Thanks. Yes.
Yes, yes, yes. Okay, great. Thank you.
Okay. Are there any more questions? Okay, it seems not. So let us thank Lorenzo again and
Thank you.
everyone who asked interesting questions. Yeah, so thank you, Lorenzo. This was very enriching.
Thanks. Okay, great.
And thank you everyone for coming. We will have the next KISS seminar on the 9th of October. I will send reminders. Pablo Arrighi will talk. Yes, then see you then. Have a nice
Okay,
day.
thank you again for the invitation. It was really nice chatting with you and
Glad.
good insights. Okay, thanks.
Thank you all. Bye.
Bye.